All right. So now that we've talked a bit about the first derivative test, we want to start preparing ourselves to look at the second derivative test, which is kind of an easier alternative if it works. Right? So before we get to that, the details of that, we need to talk a bit about concavity again. Okay? So just a reminder of what the definitions are. Right? We call a function concave up on an interval if the derivative is increasing on that interval. It's called concave down on an interval if the derivative is decreasing on that interval. So what does this look like? Okay. So let's look at some concave up stuff. Right. So I'll draw three pictures. Right. So concave up here. Remember, we want to say that the derivative is increasing. So if we look at something like an exponential function, obviously that derivative's increasing, right? I also want you to notice that this is concave up. Why is that concave up? Because the derivative is very, very negative here, but it's getting closer to zero. So the actual value of the derivative is going up, right? And then sort of we can have it where here the second derivative is all positive. Where the derivative is all positive. Here, the derivative is all negative, but that doesn't matter. Because here we're going to do where the derivative starts out negative, goes to zero, and then goes positive again. That would be something like this. Basically, what I want you to think of concave up as is sort of like, a smile, right? It's a very upward opening type graph, right? It's an upward smile. Okay? We can do the same thing for concave down. If we draw three graphs here, concave down, all right, the key thing here is the derivative needs to be decreasing. All right. Well, sort of the obvious choice would be something like this, right, where the derivative is maybe slightly negative here and then starts getting more negative. But we also have this situation here, where it starts out very positive and starts going towards zero. So again, here's an example where the derivative is positive. And then kind of overall, like these two things together, this is where the derivative goes from positive to zero, negative. Right? And why are we talking about concavity here? Well, I really want you to focus on these last two examples. Right? What do we have here and here in these examples? Right? Turns out, here, go away. Here, this looks like a local minimum, right? Here, this looks like a local maximum. The one sort of big thing we need to really think about when it comes to concavity is, well, how can we kind of identify concave up versus concave down? Right? So how we can identify that is, remember, a function is concave up on an interval if f prime is increasing. If we're asking for f prime to be increasing, that means its derivative has to be positive. In other words, f double prime of x positive. Okay? Likewise, concave down is saying the derivative needs to be a decreasing function, which means the derivative of the derivative, or the second derivative, has to be negative. So we're almost ready to state the second derivative test now. right? Here all three of these graphs have a positive second derivative the whole time. All three of these graphs have a negative second derivative the whole time. And I want you to think about how these points here are relating. All right. While that's simmering in your mind, though, let's sort of talk about, a function, right? We have its concavity. What happens when concavity changes from up to down or down to up? Right, so let's define that. Okay, so a point on a curve y equals f of x, this is called an inflection point. Right? If f, first off, is continuous there, and the curve changes from concave up to concave down, or vice versa, right? Or from concave down to concave up, right? The typical examples of that are sort of cubic functions here, right? So here this starts concave down and switches to concave up. This right here would be an inflection. Right? We could also have this graph going the other way. Starts down. Or it starts concave up and then switches to concave down. Here you would have your inflection. Right? So you can use the second derivative, right? Over here we have second derivative negative. Over here we have second derivative positive. On this side of the inflection we have second derivative positive. This side we have second derivative negative. Right? So if you look for where these derivatives are changing from concave up to down or down to up, or sorry, positive to negative or negative to positive for the second derivative, you can start identifying inflection. So let me just summarize that real quick here in a test. Right? So we have what's called the concavity test. All right. So if f double prime of x is greater than 0 for all x in an interval, then graph of f is concave up on that interval. Likewise, we have the situation for concave down. If the second derivative is negative, then the graph of f is concave down on that interval. Right? So I'll let you sort of use this to find inflection points. I won't do an example of this, but it'll look kind of similar to how we applied the first derivative. All right, and then we'll see you in the next video for the second derivative test.